before we get into finishing up transformation stuff and then get into eigenvalues and eigenvectors? Okay, yeah, let's.
Did you have a packet on Friday?
Good question. I handed out an assignment on Friday as well. Yeah. All right. All right, so right at the end of class last time, we mentioned how we would go about finding the matrix for the inverse of a transformation. So again, in order for a matrix to have an inverse, especially if we're going, let's say we have a linear operator or going from one vector space that has the same dimension as the second vector space, we said that one way to find the inverse transformation would be find a standard matrix for the given transformation. If it's 1 to 1 and onto, then it'll be row equivalent to, that matrix will be row equivalent to the identity. So then we can invert that matrix, and then that will give us the matrix for the inverse transformation. Okay. So let's look at this particular example. Well, we've got the transformation going from R3 to R3. We've got the outputs there for the transformation. First, it asks if it has an inverse. Again, if T is going to have an inverse, then it needs to be 1 to 1 and onto. So again, we check that by looking at the matrix for the transformation and row reducing, just like we always do, right? What is the standard matrix for this particular transformation? You're going down columns? Okay. Yep. I agree with that. Emily, did I give you the homework when you answered the problem?
No.
Okay. All right, so there's our standard standard matrix for the transformation. Again, we've checked if it's 1 to 1 or check if it's onto. We do both of those at the same time. If we row reduce this matrix, we should see the identity matrix, because in this case, it's going to, if it's one, it's the other, right? Since both of the input and the output spaces have the same dimension. So if I just type this in real quick to my calculator. I do get, if I do the reduced row echelon form, I do get the identity. So I do see a pivot in every column, so it's 1 to 1. I see a pivot in every row, so it's onto. So we really do get an inverse. So then we can quickly get the inverse of this matrix. If I look at the inverse of this matrix, we get 3, 3, negative 1, negative 2, negative 2, 1, negative 4, negative 5, 2. And again, the idea here is that if we take the inverse of the standard matrix for T, we get the standard matrix for the inverse of T. I use my calculator and hit inverse. I just use my calculator. I would expect that you would use your calculator to figure that out. Yeah. So now we should be able to read off what T inverse of XYZ should be. What should be the first component of the inverse in this case, looking at your matrix? Yep, exactly right. The 3x plus the 3y minus the z. Because again, we're just reading off the first row. Again, if you imagine the x, y, z being a column vector there, that's exactly what you would get when you would multiply, right? What would be the second component then? Yeah, good. The negative 2x minus 2y plus z. So then the last one must be negative 4x minus 5y plus 2z. Okay. Good. All right. So let's see if we can do the next one. In this one, we've got the transformation going from linear polynomials to two-dimensional vectors. And the way we get the output is to plug in 0 into the polynomial and plug in 1 in the polynomial and use that for our components of R2. So again, if we want to find what we're referring to here, again, this is a standard matrix here. What do we need to do? Apparently we need to sit very quietly. How do we find a matrix for a transformation? What do we plug into the transformation? A basis, right? A basis for your domain space. Since we're doing standard matrix here, we might as well use the standard basis. What's the standard basis for P1? 1 and an x, right? So if I apply the transformation to 1, what do I get out? What's the first component? Yeah, 1 and 1, right? I get 1, 1, the vector 1, 1. When you plug in x, what do we get out? 0, 1, right? Because I put 0 into x and I put 1 into x, right? Okay. Remember to find it, just generally speaking, when you're trying to find a transformation matrix with respect to bases, you put the basis vectors for the input space into your transformation, get those outputs, and then find the coordinates of those outputs with respect to the basis for the output space. Well, in this case, everything's standard basis, so the coordinates of 1, 1 with respect to the standard basis for R2 are 1, 1, right? The coordinates for 0, 1 is going to be 0, 1. So if we make this particular matrix then, we're just going to use those as columns. 1, 1, 0, 1. When we row reduce that, are we going to get the identity matrix? Yeah. It's triangular, and I already said, yes.
How come in this one we put them as columns, and then the last one we put it as rows?
So the last one we also did columns. We just did it. Remember, if you put in 1, 0, 0 here, you'll get 1. If you put in the vector 1, 0, 0, that first standard basis vector, I'll get 1, 0, 2, which is down the first column. We're doing if you read the coefficients off, those are going across the rows, but the outputs of your standard basis are in the columns. So we really are doing that each time. I don't know why that doesn't like to scroll. All right, so again, reduced row echelon form here. We would get the identity matrix, so this really is invertible. We can get the inverse pretty easily here. You can use your calculator, or remember that if you've got a 2x2 matrix, it's 1 over the determinant, and then you flip the main diagonal and negate the off diagonal. It's that, remember the formula we had with the adjoint? 1 over the determinant times the adjoint? That's what that is. In this case, the determinant is just 1. Flipping the main diagonal, I still see 1s. So then we negate the off diagonal, and I just get a -1 down below. And again, the theorem is that the inverse of the matrix for T is the matrix for T inverse. Okay. Right? Okay. So now it's asking us to find a rule then for T inverse of AB. What kind of an object should we get out of that? But in the inverse, we're going from what to what? What space do we start with when we do the inverse? Which one?
The range.
Yeah, so what is it in this case specifically? Oh,
R2.
it's R2, and what comes out? P1, right? So we need to see if actually find an honest to goodness linear polynomial that comes out, right? But if we use the matrix here, if we take 1, -1, 0, 1, and multiply it by some AB, what do we end up getting out? What's the first component going to be? A. The second one's going to be B minus A, or -A plus B, right? Remember, the whole point of being able to use matrices for the transformations is that this gives you coordinates. This is now coordinates with respect to some basis for an element in your original domain, or now what's in the range of your inverse function. Again, where is this vector supposed to live? You just told me that a second ago. P1, right? So those are going to be the coordinates, and since we use the standard basis, these will be the coordinates with respect to the standard basis for P1, right? So if I want T inverse of AB, what's the constant term going to be when it comes out? No, these are the coordinates. So what's the constant term going to be? What's your standard basis for P1 again? 1 and x. So what are we going to multiply by the 1? A. What are we going to multiply by the x? Yeah, the B minus A, the -A plus B. Yep. That's what we'll get out. These literally are your coordinates, right? This tells you what to multiply the first basis vector by. This tells you what to multiply the second basis vector by. That's why we're using the matrices here. What comes out are coordinates. Right. Questions on the process on this one at all? So we've talked a little bit about composition before. What we want to do in this particular case is remind ourselves what we mean by composition, how we find matrices with respect to composition, and then how inverses behave with respect to the composition as well. All right, so remember, what does it mean for the composition? If I want T2 composed with T1 of a vector from U, what's the definition of that? What do we do? Just with function definition, it has nothing to do with transformation specifically. What does the composition of T2 with T1 mean? Yeah, it's T2 of T1 of U, right? Put U into T1, get that output. That output then becomes an input for T2, and then get that output, right? So notice I need to do The input into here comes out here. This has to match with that one if I'm going to do T2 composed with T1. If I wanted to go the other way, if I want to go the other way around and do T1 composed with T2, this W better be the same thing as this U over here, or at least be a subset of this U, right? You want to go the other way? All right. So if we want to find the matrix, or want to find this, let's do it with respect to the matrices again. Let's find the standard matrix of T1. Let's find the standard matrix of T2. Let's do both of those. Should be able to do that one relatively straightforwardly, right? What is the standard matrix for T1 in this case? Okay. Or horizontally. It works either way in this case, doesn't it? the way it worked out, it worked either way, right? So we look at our coefficients for our x's. We have 1, 1. That would go vertically. The coefficients for the y's are 1, -1. That also goes vertically. Or you can take your coefficients off each component and go horizontally, but you'll get the same matrix. It does matter for the next one, it looks like. Yeah, maybe not. It's symmetric as well. What do you get for the next one? 2, 1, and 1, -2. We agree with those? Okay. Again, the way that your composition is defined, T2 composed with T1 is T2 of T1 of the input, whatever the input happens to be. Well, we know that we can get the output for T1 by doing matrix multiplication, use that for the input for T2, and again do matrix multiplication. So we can find the matrix for the composition simply by multiplying the matrices for T2 and T1 together. Again, this is why we like matrix notation for the transformations, because we can get all of these answers using all through matrix multiplication. Okay? So we would take our 2, 1, 1, -2 times 1, 1, 1, -1. So let's see what we get here. 2 plus 1 is 3. 2 minus 1 is 1. 1 minus 2 is -1. 1 plus 2 is 3. If I did my matrix multiplication correctly. So from the matrix now, and since we're using standard matrix here, standard bases here everywhere, we should be able to read off the outputs now, right? What will be your first component for the composition? 3x plus y, good. Yeah, we're just reading that across the row. And your second component will be, yeah, the -x plus the 3y. That makes sense, what we're doing? If I want to do the next part and do the inverse of the composition, there's a couple of ways we can think about it. Well, I've already got what the matrix is for the composition. So to find the matrix for the inverse, what do I need to do? If I already have the matrix for the transformation, to find the matrix for the inverse transformation, what do we do? Yeah, just take the inverse of the matrix, right? This matrix definitely has an inverse. What's a quick numeric check again to make sure that we have an inverse for a matrix? Yeah, so what is the AD minus BC? What do we call that? Determinant, right? You can check the determinant real quick, right? The determinant here is 10. So it definitely has an inverse. So again, the matrix for the inverse transformation is the same as the inverse of the matrix of the transformation. And now we can use that formula we just had, 1 over the determinant times the adjoint. Again, it's flip the main diagonal, negate the off diagonal. Oops. And now the problem asks us to figure out what the inverse transformation applied to xy is. It doesn't matter where I put the constant, and then we should be able to read off the components again, just like we did in the previous example, right? So what's, if I leave the 1/10 out in front, what's your first component going to be? 3x minus y, and then the other one's going to be x plus 3y. Good. And then you could distribute your 1/10 through if you really wanted to. Is that okay? Any questions on that? Bless you. Any questions on that one at all? All right. This next theorem shouldn't be a huge surprise because it's the same idea with functions, right? If we want to do the inverse of a composition, we do the composition of the inverses, but we need to reverse the order when we do that. Okay? Now think about why. One of the standard examples of that is what we call the socks shoes property. You put your socks on and then your shoes. How do you undo that process? Take your shoes off first and then your socks, otherwise you're going to get a gigantic hole in your socks. Right? I'm not saying you can't take your socks off before your shoes, you just have to rip a hole and then pull them off. Right? So it's not a huge surprise that we need to do the reverse order, but it's even better when we have the matrices, right? If I know that if I have an inverse, I can do this process by using matrices. I'm abusing the notation pretty good here, but that's okay. One side is a vector and the other side are the coordinates with respect to the vector. But we know that we can do it that way, right? We can realize it as matrix multiplication, right? We agree with that? And then again, I'm abusing the notation. I really should be writing coordinates here, but I'm going to abuse notation and do it this way anyway, because I'm not going to spend a lot of time on it. We just said that to do the matrix for the inverse, that's the inverse of the matrix for the transformation, right? I can move the inverse in and out. We also said that I can do the composition by multiplying the two matrices together. Right? That's how we do composition of transformations if we have it as a matrix. Yeah. Now notice what I have here. I've got the inverse of a product of matrices. How do you do the inverse of a product? Doing this for a review more than anything. If I want the inverse of a product, what do? It distributes, and then what else do you have to do? You got to reverse it, right? You got to flip the order, right? So this is
T1 inverse, T2 inverse times this same matrix here as a column. And then again, I can move the inverse back inside. Then this is the matrix for the composition. Since I got a product of matrices, that's the same thing as the matrix for the composition. And so this will be T1 inverse composed with T2 inverse of our X. So notice I went through all of this just by doing matrix multiplication. Again, I'm really talking about coordinates. So those last two steps, excuse me, try that again. The first step and the last step. This, really, I should have coordinate vectors around all this stuff. And here as well. These would be the coordinates of X with respect to the basis. But the process is just going through that idea there. So again, for transformations, it works nicely with this particular proof. I don't have to do a lot of work to get to it. Again, shouldn't be a huge surprise because this is also true for any functions that you come across. If you've got one-to-one functions f and g, and you want to invert the composition of f with g, it's going to be g inverse f inverse, the other way around. So it gets flipped. All right. So let's do one more example here, and this will be the last example we'll do for transformations, and we'll kick over to eigenvalues and eigenvectors, and that'll be what we'll end the semester on. Again, we want to do this with matrices. So we've got T1 does the derivative of the product of x with p of x, and then T2 takes p of x and translates it left 1 unit. That's what p of x plus 1 does, right? Graphically, we'll just shift everything to the left 1 unit, right? Okay. All right, so this one says, let's see if we can find the derivative of x times p of x. So we have to multiply by x first and then differentiate, right? Not the other way around. It doesn't say take the derivative of the function and then multiply by x, because that wouldn't be 1-to-1. Because anytime I differentiate a constant, I would get 0. Right? So that wouldn't be 1-to-1. I need to go this way. All right, so remember again how we find our standard matrices. We want to plug in the standard basis first. Our standard basis for P2 is 1x and x squared. So I'll put 1x and x squared into T1, and I'll put 1x and x squared into T2. That's the first step, right? Anytime I want to find a matrix for a transformation, the first thing I'm going to do is put in the basis vectors that I'm given into the transformation and get outputs for the basis vectors. In this case, we're not given basis vectors, so we'll assume we'll use the standard basis. And remember again, for T1, the first thing we're going to do is multiply the function by x and then take the derivative. Multiply 1 by x, we get x. Differentiate, we get 1. Good. The second one, we'll multiply x by x to get, and differentiate, we get 2x. Good. Multiply x squared by x, we get, and then differentiate 3x squared. Good. What do we get then for the standard matrix for T1? What will your first column be? 1, 0, 0. Because again, we're getting the coordinates of this with respect to the P2 again, right? The second column will be 0, 2, 0. The last column will be 0, 0, 3, right? That matrix invertible? Yeah. It's triangular. So how do you take the determinant of a triangular matrix? Multiply that with a diagonal. Whenever you've got a triangular matrix, you can just multiply down the diagonal. Notice I'm trying to review some things as we go along. I'm clever like that. All right, the next one, the next transformation, T2, is shift the polynomial left by 1, or replace x with x plus 1, right? Well, if I replace x with x plus 1 on the first one, what do I get? 1. Second one I get x plus 1. I'll write it as 1 plus x because we usually think of our standard basis as being 1x squared. For x squared, what do we get? Yeah, 1 plus x quantity squared, right? The x gets replaced with 1 plus x. If I FOIL, you get 1 plus 2x plus x squared. What's your matrix then? Everybody okay with that matrix? What's its determinant? 1. Yeah, good. Just multiply it on the diagonal again. So far, so good? We happy? As happy as you can be in linear? Okay. All right. Matrix for the composition. How do we find the matrix for the composition? Multiply. Good. Yeah, multiply the two matrices together. I need the matrix for T2 times the matrix for T1 this way. Notice we've got a diagonal matrix here being multiplied on the right. So the effect of this multiplication is just multiply 1 times the first column, 2 times the second column, and 3 times the third column. When we multiply by a diagonal matrix on the right, we end up multiplying the columns by those constants. We did it on the left to be the rows. So we end up with 1, 0, 0, 2, 2, 0, 3, 6, 3. Okay? Is that okay? There's our matrix for our composition. If I have some polynomial, and we multiply by, say, some a, b, c, where a is the constant term, b is the coefficient on the x, c is the coefficient on the x squared, your first component would be what? It would be a plus 2b plus 3c, reading across here, right? Because I take that row times the abc. The next one would be 2b plus 6c. And the last one would be 3c. Again, the answers here that we get are the coordinate vector. They're the coordinates of the output with respect to the basis in your codomain. Well, our codomain still is P2, so those are coordinates with respect to P2. So what's your constant term of the output going to be? What's the constant term going to be for your output? These are coordinates with respect to the standard basis. 1x squared. What's your constant term going to be? A plus 2b plus 3c. What's the coefficient on the x term going to be? 2b plus 6c. What's the coefficient on the x squared term going to be? 3c, yeah. Those are the coefficients. That's the constant, the x, and the x squared coefficients. So this will be a plus 2b plus 3c plus 2b plus 6c times x plus 3c times x squared. They are the coordinates. That's the whole point of doing this. They give you the coordinates for your output vector. The output space is P2. There you have it. The last thing it asks you for here is what? It says it also wants the inverse How do we find the matrix for the inverse? Okay, the inverse of the matrix, good. Okay, so if I want the matrix of the inverse transformation, I take the matrix of the transformation and invert it. Put that in your calculator. That's what you should get for the inverse. So now we should be able to read off, hopefully, we're paying attention. We should be able to read off the constant term, the x term, and the x squared term here. Notice in the previous part, you see any correlation here with the A, the 2B, and the 3C, and the matrix we're starting with? Where'd the coefficients on the A, B, and C come from? The diagonal? I mean, it looks like the diagonal. How about the second one, the 2B and the 2B and the 6C? It's the rows, right? Because again, when we multiply down this column, the rows get multiplied, right? So first row gets multiplied by A, B, C, there it goes. Second row gets multiplied by A, B, C, there it goes. Right? And then these were constant x squared term. So you should now be able to tell me what the constant, the x, and the x squared term are, given an A, B, C, looking at your matrix. What's your constant term going to be? Yeah, it's A minus B plus C. What's your coefficient on your x term going to be? Yeah, B over 2 minus C times x, and your coefficient on your x squared? 1/3. That'd be C. So yeah, it'd be C over 3. Good. And x squared. Again, remember, we're thinking about the A, B, C being over here on the side, right? And again, the outputs that you get are the coefficients, are the coordinates that you want, and those turn out to be the coefficients. Questions on that one at all? All right. So let's switch gears a little bit here. You're welcome. Second to last handout you're going to get. We're almost done. There you go. All right. So let's, we've already talked about eigenvalues and eigenvectors before, but let's remind ourselves what we mean here. The whole goal of eigenvalues and eigenvectors is to be able to replace matrix multiplication with scalar multiplication. So if I have a matrix A and a vector V, then V is an eigenvector of A if there exists a scalar lambda such that A times V is equal to lambda times V. We've talked about eigenvalues and eigenvectors before. Lambda is called an eigenvalue for A. V is called an eigenvector for V, A. We did this before when we did determinants. Remember? It's been a little while. I'm sure you've all slept since then, but you are college students. I can't be 100% certain of that. Okay. All right. But we've talked about this before. So let's remind ourselves of looking at this from a definitional standpoint. I've got a matrix A here. I've got vectors V1, V2, V3 here. If I take my A times my V1, notice here I get 0, 1, 0 when I multiply, right? Notice it matches up, right? That 0 hits that 1, and the other two zeros kill those off. That 1 hits that 1, and then again the 0 matches up with the 1. So is the output, now what we're looking for here is the output a scalar multiple? Is the answer a scalar multiple of the thing we started with? Yeah. Okay. What's the lambda? 1. Good. So 0, 1, 0 is an eigenvector of A corresponding to lambda equals 1. Let's do the next product. So I'll take the matrix A and multiply it by the V2. When we take the first row times that column, looks like we get -2. When we take the second row times that column, looks like we get 4. And take the last row and multiply it by that column vector, looks like we also get 4. So again, is the answer a scalar multiple of what we started with? What scalar? 2, yeah. So -1, 2, 2 is also an eigenvector. I guess "and" would be a better word than An eigenvector, try to get the grammar correct, of A corresponding to lambda equals 2. And just to finish it off, since I did give you 3 vectors, when we multiply this one, what do we get? -4 times -1 gives us 4, and then +1 gives us 5. All right, yeah, okay. 2 plus 1 gives me 3, and then 2. The 4 is not negative. That's what my problem is. Thank you. So I get -3. Couldn't believe I didn't give you another one that worked. Thank you. That does make a difference. All right, so again, last thing, is this an eigenvector then? Yes. What's the lambda corresponding to it? What's the eigenvalue corresponding? 3. Yeah, so -3, 3, 3 is an eigenvector of A. I can spell eigenvector of of A corresponding to lambda equals 3. Now, if they weren't constant multiples of each other, then you would say it's not an eigenvector, right? So had it really been a negative 4 that was multiplying by, that wouldn't have been an eigenvector. So,
Why is the second one used the vector that we were given, but in the third one we used the vector that we got from multiplication?
it doesn't matter which one I use, but you're right. I should use the vector that I was given. Sorry. I was looking at the answer. Yeah. In this particular case, it wouldn't have mattered. They're both eigenvectors. Yeah. If something is an eigenvector, then a scalar times it will also be an eigenvector as well. So, okay. All right. All right, just real quick here in the last few minutes, just to remind how we find these things. We've already gone through this before. I know it's been a month or two, but we've already talked about this before. The whole idea is that when we want to find these things, I want to solve this system. Again, the whole goal of this is to replace matrix multiplication with scalar multiplication. So I want to find all the vectors that I can do that with, right? That's the idea. So we want to solve this particular system, and we want non-trivial solutions. Certainly if I put the 0 vector in on both sides, I get 1. That's not interesting, right? That's not the interesting case. So just like what you would do back in algebra class, let's gather our x's to one side. I'd love to be able to factor off the x. Whoa, I'd love that not to scroll on me when I'm not doing anything. I'd love to be able to factor off the x. The problem here is this is a matrix and that's a scalar, right? So before we factor that off, we need to stick an identity matrix in there. We've talked about this before. It's been a while, but we've talked about this before. So this is now a homogeneous system that we've created. If this only has the trivial solution, what's true about this matrix? If we only have the trivial solution, what's true about this matrix A minus lambda I? What's that again?
Never mind.
No, I think you were saying the right thing. What'd you say?
If the determinant is not 0.
Yeah, the determinant's not 0 if it's invertible, right? If it's invertible, this will have only the trivial solution, right? If I can move this to the other side. So we want that thing to not be invertible, so we want its determinant to be 0. That's exactly right. So that's how we get what we refer to that as that characteristic equation. So we want A minus lambda I to be singular. Remember that word, singular? And not from English class. What we mean, right? Not invertible. So we want the determinant of A minus lambda I to be 0. So that's exactly what we mean by the characteristic equation. The characteristic equation is set the determinant equal to 0. When we take remember lambda I is the matrix that just has lambdas down the diagonal and zeros everywhere else. So that A minus lambda I has the effect of subtracting lambda off the diagonal. When we take the determinant, we'll get powers of lambda everywhere, right? So the characteristic polynomial is just that determinant. We get a polynomial in lambda. So when we say we want the characteristic polynomial, that's what we mean. So for Wednesday, what I would like you to do is figure out what the characteristic polynomial is for this A that's on here. You can stop at that point. If you want to go ahead and figure out what the eigenvalues and eigenvectors are, great. You should get the same answer that we had in the example. But I just want you to go through the practice of finding the characteristic polynomial here for this one. Okay? All right. We'll talk about that next time. Have a good one.
Curious what's gonna go.